This is section 16.3 on the fundamental theorem of calculus for line integrals, somewhat similar to the fundamental theorem of calculus we had in Calc 1 and 2. Share the screen. Get this thing focused. All right, so the fundamental theorem of calculus for line integrals, page 1087. So look at box 1, that's what we had in Calc 1 and 2. Integral from a to b of f prime of x dx is capital F of b minus capital F of a, which means anti-differentiate, plug into b, plug in a. So we have something similar. Theorem 2, you can put this on your cheat sheet. Let C be a smooth curve given by the vector function r of t going from a to b. Let little f be a differentiable function of 2 or 3 variables whose gradient vector del f is continuous on C. Then the integral along C of del f dot dr is f of r of b minus f of r of a. In essence, all the functions you're dealing with satisfy this. So this is all you really need. Okay. So integral of del f dot dr is f of r of b minus f of r of a. Okay. Where this is the gradient, so you're kind of doing an anti-gradient, as it were. Okay. And the picture is something like A or B, three-dimensional, two-dimensional, three-dimensional flavor. Okay, so you're integrating along such a curve. All right, so we have some terms that we have to talk about. All of these turn out to be equivalent. On page 1088, independence of path or path independence. Okay, the concept of path independence is that as long as you have the same initial and final points, okay, the integral is path independent if the integral along C1 of del f dot dr is the same as the integral along C2 of del f dot dr, regardless of what path you pick. So if you have one beginning point, one ending point, doesn't matter how you go from point A to point B, you can go like that, or go in a straight line, or squiggle all over and go a million miles there and come back and land there. You end up with the same answer. Then you have something called path independence. Okay, and by definition, you have something called a conservative vector field. And this leads to the laws of conservation that we have in physics. Conservation of energy, conservation of charge, conservation of momentum, conservation of angular momentum. And so all the conservative laws that we have in physics. Okay, energy is a big one. Conservation of energy, potential energy perhaps. So if you start at a point here and you end up here, doesn't matter how you go from this point to this point, the change in potential energy would be exactly the same. So that leads to conservation. You have conservative vector field, as it's called. Okay, and that leads to something called path independence. Integral along C1 is the same as integral along C2 for any two paths, C1 and C2, as long as you have the same initial and terminal points. Okay, and on page 1089, a curve is called closed if its terminal point coincides with the initial point. So here's a closed curve, obviously. And then a natural result of that, if you have path independence, integral along C of f dot dr, the work done, is independent of path if and only if the integral of f dot dr is 0 for every closed path C in D. So if you start here, you end there. Well, if the path doesn't matter, if you move nowhere, then the integral should be 0. But if you go all around the place and end up at the same spot, then the answer is still 0 if you have path independence. Okay? So if you start here and wiggle whatever and come back to the same spot, you've got the same amount of kinetic energy or potential energy, as the case may be, or whatever conservative vector field you happen to be talking about. Okay, then we have this theorem here, and on page 1089. So suppose f is a vector field continuous on an open connected region D. If the integral along the curve of f dot dr is independent as path, then f is a conservative vector field that means there exists a function little f, I call it the anti-gradient, such that del f, gradient of f, is bold f. So you can find something called an anti-gradient. So we know how to find a gradient. We're going to do anti-gradients right now also. Okay. Now, in 2 dimensions, page 1090, how can we tell if we have path independence or conservative vector field? So we have this theorem. In 2 dimensions, if f is pq, pi plus qj, if it's a conservative vector field, where p and q have continuous first order partial derivatives, that's always going to be the case in the problems that we do. Then a partial p with respect to y is equal to partial of q with respect to x in 2 dimensions. There's another root for 3 dimensions, a little bit harder, but that has to be true in 2 dimensions. Okay, the converse is also true. Namely, on page 1091, if f is pi plus qj on an open, simply connected region, suppose p and q have continuous first order partials, and this is true, p sub y equals q sub x, then f is conservative. It's kind of a quick explanation as to why that works. Suppose you have a conservative vector field, okay, then that means there is a function little f such that p is fx, q is fy. Well, by Clairaut's theorem, we know that the second partial with respect to y and then with respect to x is equal to the second partial with respect to x and then with respect to y. Okay, which means this p already being the partial with respect to y, if I now differentiate with respect to y, I will get the same thing here as if I differentiate this with respect to y and differentiate one more time with respect to x. So when you are presented a problem with a conservative vector field, you're at the first level of the derivative, so to speak. You've got this anti-gradient here. You've got the gradient vector. Okay? And then if the partial of p with respect to y equals a partial of q with respect to x, that means by Clairaut's theorem, okay, they're going to be equal to each other. So you do have a conservative vector field. So in a nutshell, how do we determine in 2D if a vector function is conservative? If the partial of p with respect to y equals the partial of q with respect to x. Okay, and we'll be doing some of those kinds of problems. Okay, then the text talks about conservation of energy, page 1093. You can read more about that in your physics book, of course, but all the conservation laws, conservation of momentum, conservation of electric charge, perhaps, angular momentum. Okay, so the various conservative laws that we have in physics. All right, so let's get started. So 16.3 to 21, I guess. So page 1094. All right, so do we have a conservative vector field or not? And if we do, find the anti-gradient, find a function little f, for which that's going to be true. 13, 15, 17, 19, 21. Okay. All right, number 3. F of xy is xy plus y squared I, x squared plus 2xyj. Is it conservative? So partial of p with respect to y, x plus 2y. Partial of q with respect to x, 2x plus 2y. They're not equal. Therefore, f is not conservative. We're done. We cannot find an anti-gradient. There is no little f such that the gradient of little f is this. In other words, this cannot be the answer to a gradient problem. Okay, so that was too easy because it's not conservative. So most of the rest of them, they are conservative. Okay, so f, number 5, y squared e to the xy, 1 plus xy e to the xy. Okay, so the partial of p with respect to y, product rule. First times the root of the second, y squared times e to the xy times an extra x, plus second times the root of the first, e to the xy, 2y. Factor out the e to the xy, xy squared plus 2y. What's the partial of q with respect to x? Product rule. first times the derivative of the second with respect to x, 1 plus xy, e to the xy times y, plus the second e to the xy times the derivative of the first with respect to x is y. A little bit of cleanup, e to the xy, distribute y plus xy squared plus y, or 2y plus xy squared e to the xy. They are equal, therefore f is conservative. Okay. So now for the new part, find the anti-gradient. This was the answer to a gradient problem. What is the original little f? Okay, so here's what you do. This was fx. So fx is y squared e to the xy. So I integrate with respect to y. And if you look at this, if I ask for the derivative with respect to x, I'll multiply by an extra y. So if I integrate, I divide by y. In other words, y squared divided by y, e to the xy. But you might also have a function of y, g of y, because if I have some function that only has y, it can be y squared, tangent y, square root of y. The derivative with respect to x is 0. So I got to have a whole bunch of stuff involving y. Okay, by the way, double check this, y e to the xy. What is the derivative with respect to y? Well, it's the same thing times an extra, I'm sorry, what's the derivative with respect to x? It's the same thing times an extra y squared e to the xy, plus g of y. And the derivative of this with respect to x is 0. Okay, now what you do is differentiate with respect to y. So derivative of this with respect to y is just g prime of y. Derivative of this with respect to y, product rule. First times derivative of the second with respect to y is x, so xy e to the xy, plus the second times the root of the first, e to the xy, plus g prime of y. And if I factor out an e to the xy, I get 1 plus xy plus g prime of y. And that is supposed to be equal to the given 1 plus xy e to the xy. Well, that is exactly the same as that, which means g prime of y should be 0, or g of y is a constant. Okay, so we're done. F of xy is y e to the xy plus k. This is the same as plus c. Remember in Calc 1 and Calc 2 when we were integrating, we had blah, blah, blah plus c. For some reason, Mr. Stewart changes it to plus k. It's really the same thing, but k can be any constant. Okay, so the gradient of any of these functions is this. Of course, the derivative of k is easy at 0. But if I differentiate with respect to x, I get the same thing times y. So xy plus y squared. And if I differentiate with respect to y, you get a product root, but it should also work. Okay. Looking at this one, sorry. All right, 9. F is this. P, Q. Partial P with respect to y. 2y cosine x minus sine y. Partial Q with respect to x. 2y cosine x minus sine y. Same thing. Therefore, F is conservative. We can find an anti-gradient. That means this is fx, this is fy. So fx is y squared cosine x plus cosine y. So first I integrate with respect to x. So y squared sine x plus x cosine y plus a function of y, g of y. Remember, this can have a whole bunch of stuff involving y. The derivative with respect to x is 0. Now I differentiate with respect to y. 2y sine x minus x sine y plus g prime of y. And I set it equal to this thing, 2y sine x minus x sine y. Once again, that is the same as that, meaning g prime of y is 0. So g of y is just any constant. So f of xy is y squared sine x plus x cosine y plus any constant. Okay, the gradient of any of these functions is this. So the partial with respect to x, you can double check is that. The partial with respect to y comes out to be that. Okay, in this particular case, there is no anti-gradient. Okay, this is not the answer to any gradient problem. Okay, 11 is a little bit different. I'll show you this. So The vector field is f of xy, 2xy, x squared. There's three curves that start at 1, 2, and at 3, 2. So you can go like that, you can squiggle like that, or you go like that. Explain why integral along C of f dot dr has the same value for all three curves. Well, the only way that's going to work is if you have a conservative vector field. So we have to show that this is a conservative vector field. And part B, what is this common value? So that's where the fundamental theorem of calculus comes in. So once I find my anti-gradient, I plug in 3, 2, I plug in 1, 2, and subtract. Okay. All right, so the partial of P with respect to Y, 2x. Partial of Q with respect to X, 2x. Therefore, F is conservative, that dot is conservative. That means we have path independence. So it doesn't matter which path you pick, you get the same answer. So that's Fx, that's Fy. So Fx is 2xy. Integrate with respect to x, that's x squared y plus g of y. Differentiate with respect to y, x squared plus g prime of y. Set it equal to x squared. Once again, that means g prime of y is 0. So g of y is k. Since I can let k be any real number, well, just like in Calc 1 and Calc 2, what's the easiest k to pick? 0. So use f of xy is x squared y. Double check. What's the gradient of this? Derivative with respect to x, 2xy. Derivative with respect to y, x squared. So it doesn't matter what path I pick. So what is the value of the work done? The work done, okay. Just put f of 3, 2 minus f of 1, 2. Fundamental theorem of calculus. Okay, so I plug in here. So plug in 3, 2, 9 times 2. Plug in 1, 2, 1 times 2. So 18 minus 2. Final answer is 16. Okay, so 13 f of xy is that. The curve is r of t is t cubed minus 2t, t cubed plus 2t, t going from 0 to 1. Okay, now, if we have a conservative vector field, then it doesn't matter what path I pick. Okay, so I'm not even going to fool with this. Let's see if we have a conservative vector field. Oh, actually, yeah, for 13. They already tell you that it's a conservative vector field. So I can just go to it. Now, 15 is also conservative because they're telling you you can find an anti-gradient. We don't know how to determine in 3 dimensions yet whether we have a conservative vector field, but we got that in a future section. Okay. Now, 13, I do need to know where I start. So I plug in 0, 0, 0. Plug in 1. 1 minus 2 is negative 1, and 1 plus 2 is 3. So I'm going from 0, 0 to negative 1, 3. All right, so this is fx. Integrate with respect to x. 1/3 x cubed y cubed plus g of y. Differentiate with respect to y. X cubed y squared plus g prime of y. Set that equal to x cubed y squared. Once again, in this case, it's easy. G prime of y is 0. So I'll decide to use 1/3 x cubed y cubed. In other words, let k be 0. Double check. What's the derivative with respect to x? That. What's the derivative with respect to y? That. So now by the fundamental theorem of calculus for line integrals, all I do is plug in negative 1, 3 here, plug in 0, 0, and subtract. Plug in 0, 0 is easy, you get 0. So negative 1, 3, 1/3 of negative 1 times 3 cubed comes out to be negative 9. So the answer is negative 9. That's okay. The answer can come out to be negative. That's certainly allowed. Okay. 17. Now 17, they already told us, oops, that you have a conservative vector field. Okay, we don't know how to determine it yet, but they're telling you it's conservative, so we can go right to it. So I need my starting point. I don't really care about the path. We have path independence for conservative vector field. So where do I start? Plug in 0, 1, negative 1, 0. Plug in 2. Let's see, 4 plus 1 is 5. 4 minus 1 is 3. And 4 minus 4 is 0. So I'm starting at 5, 3, 0, and I'm ending at 1, negative 1, 0. That's fx, fy, fz. So integrate with respect to x. Okay, so if I differentiate with respect to x, I would multiply by z. Since I'm integrating with respect to x, I lose the z or divide by z. So y e to the xz plus g of y z. Okay, first, what's the derivative of this with respect to x? You would multiply by z, so it works. And what does that mean? That means I can now have a function of y and z. I can y squared z cubed minus sine y plus e to the z y ln y. Doesn't matter. The derivative with respect to x is 0. So that's why I have to put this down. Now I differentiate with respect to y, e to the xz plus gy. And it's supposed to equal e to the xz. Well, that means g of y is 0. Perfect. So this doesn't have any y, but it potentially still could have a z. So now f of x, y, z is y e to the xe plus h of z. Now I differentiate with respect to z. It's the same thing times an x. So xy e to the xe plus h prime of z. And I set it equal to this, xy e to the xe. Well, once again, that means h prime of z is 0, which means h of z is a k. So the best thing to use is y e to the xz. Okay, and I'll let you double check if the gradient of this is indeed this, right? Derivative with respect to x, multiply by an extra z. Yep. Derivative with respect to y, just lose the y e to the xz. Differentiate with respect to z, multiply by x. Perfect. Now, what is the value of the integral? We have path independence, so you don't have to go through the path that they give me. I just need the ending point, starting point, plug in. So 530. So 530. 0 here means that's 1, so 3. Minus 1, negative 1, 0. 0 there makes that a 1. And that negative 1 gives me a negative 1. So 3 minus a negative 1, the answer is 4. $19. So that the line integral is independent of path, evaluate the integral. So this is pdx plus qdy, or f dot dr. Any path from 1, 0 to 2, 1. That means this better be conservative, because if it's not conservative, you won't be able to do it. All right, so this is p, that's q. P dx plus q dy, f dot dr. All right, so do we have a conservative vector field? So partial of q with respect to x is negative 2x e to the y. Partial of p with respect to y is negative 2x e negative 1. They're the same, therefore f is conservative. So this is fx. Integrate with respect to x. X squared e to negative y plus g of y. Differentiate with respect to y. Same thing times negative 1. Negative x squared e to negative y. I got to set it equal to negative x squared e to the negative y, and this has a g prime of y. So once again, that makes g prime. Oh, I'm sorry. Yeah, this is our first instance where it's not trivial. I have negative x squared e to negative y plus g prime of y is equal to 2y, where'd it go? 2y minus x squared e to negative y. So that's the same as that. That forces g prime of y to be 2y, which means g of y is y squared plus k. Guess what k I'm going to use? 0. So that means f of xy is x squared e to negative y plus y squared. Okay, double check the gradient of this is this. Partial with respect to x is that. Partial with respect to y is that. All right, now I'm going from 1, 0 to 2, 1. So plug in 2, 1, f of 2, 1 minus f of 1, 0. So plug in 2 here, 4 e to the negative 1 plus, plug in 1, you get 1 minus let's see, minus 1. Okay, so plug in 1, 0, that's 0. That's going to be 1. So the 1's cancel out. So the answer is just 4 over e. Okay, finally 21. Suppose you're asked to determine the curve that requires the least work for force F to move from particle from one point to another point. You decide to check whether F is conservative. And indeed, it turns out that it is conservative. How would you apply it to this request? Well, because of path independence for conservative vector fields, it doesn't matter which path is chosen. You can't improve. It's going to be the same answer no matter what. Okay, so that was section 16.3.